Now we're going to give some examples of how you do a procedure call, and we're going to talk a little bit more detailed about how the stack works. So here we have some code. We have a caller and a callee, and we want to take a look at which registers each one of these needs to save. So let's take a look at the caller first. So here's the question: what resources does the caller use? So to answer this question, we need to look at which registers the caller is using. So we can see here they are. It's reading data from T0, S0, S1, T0, and T0. So that means that the caller is using those registers, T0, S0, and S1. Now what resources does the callee use? So for the callee, it's a little bit different. We want to look at what registers the callee writes to, because those are the things that are going to mess up the registers in the caller. So in this case, the callee is going to write to T0, T1, and S0. So now that we know which resources the caller and the callee use, now we can start thinking about which one has to save which registers according to the convention for MIPS. So what does the caller need to save? Remember what we said, the caller needs to save anything not in the S registers. So if we look at the data that the caller is using, it's only got one register that's not an S register that it's using, and that's T0. So the caller is going to have to save T0. Now correspondingly, what does the callee need to save? So the callee needs to save anything that is in the S registers. So we know the callee uses one S register, and that's S0. So now we figured out which each of these needs to save. The caller needs to save T0, and the callee needs to save S0. Now how do we actually go about saving these registers? The way we're going to save them is we're going to use the stack. And the stack is just a part of memory for storing temporary data, and it looks like this. Here we've got a stack, and you can see the stack is starting at the top and growing down. There's a stack pointer, which is kept in the SP register, which points to the end of the stack in memory. So it's going to point here. And as I mentioned, in MIPS the stack is going to grow down, but logically it doesn't matter if it grows up or down. So how do we use this? Well, procedures move the stack pointer when they store data on the stack, and then they can store the data there. So here's our stack before we call the procedure. Now when we go ahead and call the procedure call, the procedure is going to move the stack pointer, and then it's going to use that place on the stack to store some of its data. Here the callee might save S0. Here it's going to move it again, save another value, move it again, save another value, etc. So here the callee saved 4 values on the stack, and it's done that by moving the stack pointer and writing the values to that location in memory. Now, when the procedure is done, the callee has to return the stack to the way it was before. So after the procedure call, it's going to read those values in from memory, put them back into the right register files, move the stack pointer back to where it was expected, and then go ahead and return to the caller. So the stack gives procedures a secure place to put their data that doesn't fit in registers. Each procedure manages their own stack space so they don't interfere. Your stack space is below the stack space of whatever called you. And this works great as long as you return the stack to the way it was before. If you mess up the stack that's not yours, so if a callee messes up the caller data, then the program is going to crash because the caller isn't going to get the right data. So let's take a look at an example of how you save things to the stack. Here's the same program we had before, and we know that the caller is going to need to save T0. So how does it do that? Well, we're going to do it with these instructions here. We've got add I, stack pointer, -4, right here. And so what we're doing is we're moving the stack pointer down by 4, moving it down by 4 bytes or 1 word, and then we're doing store word. We're storing T0 to the stack pointer. So this is going to save T0 onto the stack and move the stack pointer down by 1 location. Then when we do ahead and call our procedure, here we have the call to the leaf function. When we're done with that, we need to restore it. And not surprisingly, we're going to do load word from the stack pointer. So this is going to say, take the data I wrote to stack pointer and store it, read it back in and put it in T0, and then I'm going to add 4 to the stack pointer. I'm going to put the stack pointer back where it was. So after I make my call, I'm going to read the registers I stored onto the stack back. Then I'm going to move the stack pointer back to where it was before. Now let's take a look at what happens in the leaf example. For the callee. remember the callee needs to save S0. So it's going to do the same thing. It's going to move the stack pointer down by 4 and store S0, and then when it's all done, it's going to read S0 back in from memory, write it into the register, and then put the stack pointer back where it was before. Okay? So let's walk through this in more detail and ask some questions about it. So we've identified the caller uses T0, S0, and S1, and T0 is not saved, so the caller has to save it. So we know the caller is going to have to save it there because it's not a saved register. What about S0 and S1? Why aren't we saving those? Well, S0 and S1 are callee saved, so the caller doesn't need to save them. It will be the callee who has to save them if it uses them. So after we've done the call, the caller is going to restore T0, and the result is in V0. So the result is in V0 because that's one of the registers for returning the results. And here's a question, why didn't we save T2? We're using T2 down here, but we didn't save it anywhere. And the reason for this is we overwrite T2. We copy the result from V0 from the procedure into T2, so we don't care if the callee messes up T2 because we're overwriting it. So what happens in the callee? Well, the callee starts off and all of its arguments are in A0 through A3. It's using S0, so the callee has to save it. So it pushes S0 onto the stack and moves the stack pointer down. What about S1? Do we need to save S1 here? Well, the callee never writes to S1. So if the caller is using it, we're never going to change it, so we don't need to save it. When the callee is done, we place the results in V0 because that's the result register we're going to return it into. And then we restore S0 because we might have changed it. So we load it, pop it off of the stack, and move the stack pointer back to where it was before. So this is how this program works. You want to make sure you walk through this carefully so you understand this. Alright, so let's take a look at the stack when we have multiple callers and callees. So here's the beginning of a program. We start off in main. Then we're going to call procedure B, and we call that by doing jump and link to B. And then inside of B, we're going to call jump and link to C, and then we'll finish C at some point and call jump return. We'll finish B at some point, call jump return, and then we continue to main. So let's take a look at what our stacks look like at each of the points in this program. So main is going to have some data on the stack, and it's colored gray here. You can see here's the data from main. Now when we call B, when we go into this procedure, B is going to store some stuff on the stack. It's going to store the registers from main that it needs to use so that it doesn't overwrite them. When we call C, C is going to store more data on the stack. It may need to save registers from B so that it doesn't overwrite them. But then finally, when C is done, it's going to pop that stuff off the stack. It's going to take those registers, restore them so B has it the way it expects them, return the stack to the way it was, and when we leave C, you see that the stack goes back to just the way B was expecting it. And this is really important. The stack is returned to the way B had it before C was called. So C can do whatever it wants with the stack. It can call any other procedures, which might change the stack again, but it has to return the stack to the way B was expecting it. Similarly, when B finishes, it returns the stack to the way main was expecting it. So what you see here is that the stack is growing and shrinking as you call different procedures. Each time you call a procedure, it's going to push more data onto the stack and move the stack pointer down, and when it finishes, it's going to remove the data from the stack and pull the stack pointer up again. So an interesting thing to note here is some machines provide stacks as part of the architecture. So VAX machines did this. The Java virtual machine provides a stack as part of its architecture. Others are implementing them in software, and that's what we've seen in MIPS. Following this convention of keeping the stack pointer and having procedures use it like this, we get stacks in software on MIPS. So let's take a summary of procedure calls. Procedures are needed to make sure we don't corrupt caller resources. So we can call into another place of code, and we need to make sure that we don't mess up the registers that were being used by the caller. We also need to make sure we get back to the right place we were at. So when we jump to a procedure, we need to store the location right after we jumped from so we can jump back to the right place when we're done. To accomplish these things, we have conventions for who saves registers. So to make sure we don't corrupt registers, we make sure we know if the callee or the caller is supposed to store registers, and to store them, we store them safely on the stack. We use JAL and jump return to enter and exit procedures because these keep track of where you're jumping from so that you can jump back. And basically, as long as everybody follows this convention, we get interoperability. Any caller can call any callee and vice versa.